ओके म्यूट कर दें, ठीक है?
रहने दीजिए, कोई प्रॉब्लम नहीं। चलो अमित जी किधर से? देवगन। और बाकी लोग नहीं है?
नहीं जाएंगे। उनका टाइम
So good afternoon, Amit ji. Can you hear me? Good afternoon, Amit ji. आपको सुना, आवाज जा रहा है आपको? Okay. Okay. So so I will start at 505. Okay. Next 2 minutes I will start. So okay, so today I'm going to start where I left in the last class. So last class I have discussed one of the very interesting example where you can see I have discussed about a molecule which is this is the Fisher projection formula of that particular molecules. And I told this molecule have a meso compound. Okay. So how can I say this is a meso, this is a enantiomer and this kind of things? Meso compound is very simple because if this molecule have a mirror image in relationship of the one half of the molecule to the other section, because if you put a mirror here, this one will be mirror image, this one will be mirror image of this one will be mirror image of this one. Okay, so if I return such kind of molecules like this way, CO2H, CH, OH, and CO2H. So this molecule have two chiral center. This is the two chiral center of the molecule. The chiral center logic I have already explained in the last class. If a center have a B, C, D, four different substitution and A not equal to B, not equal to C, not equal to D, then we call this center is a chiral. Okay. The general formula is how many kind of isomer, how many stereoisomer is possible in a molecule. If I given this kind of molecules, how many stereoisomer is possible? The formula is 2 to the power n. Okay, so this molecule have how many chiral center? N equal to number of chiral center. N equal to number of chiral center. So this molecule have a two chiral centers. So the result will be 2 to the power 2. That means 4. Okay. Post you will get the eigenvalues. But there is a little difference there. If your substitutions, if your connectivity is, sorry, so if your connectivity is क्या हो रहा है? Okay, if your connectivity is CAB, CABC and CABC. What is the meaning of CABC, CABC? That means your three substitute and because your this center have a CABCD. If you consider this one, that means I check it. It's on. Okay. So that means what you are getting? That means your is very similar type of connectivity is there. Okay. Why I'm saying similar connectivity? See here. This center have a connectivity is CHOH, 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 CO2H, CHOH, CHOH, CO2H. So that means if you have a similar kind of connectivity, then formula will be little bit change. So your new formula will be CABC kind of connectivity will be there. Then your new formula will be 2 to the power n plus 2 to the power n minus 2 by 2. Okay, so that means the molecule have a CHOH. The previous molecule have a CHOH, CO2H, and CHOH, CO2H. Similar kind of connectivity. What I'm explaining in that cases. So then n equal to 2 because the chiral center is 2, but total number of stereoisomer will be 2 to the power n. So that is 2 to the power n minus 2h. Okay. Okay, so just a minute. It will be okay. So I'm written wrong. So first is 2 to the power n minus 1 plus 2 to the power n minus 2. So 2 to the power n minus 1 means 2 minus 1 plus 2 to the power 2 minus 2 by 2. So 2 to the power n minus 1 means 2. So you will get 2 plus 2 to the power 0 means that is 1. So that means you will get instead of 4, you will get 3 stereoisomers. This is a very interesting point. Why I'm saying. So already all of you seen the one is this one. Okay. So one is which one? CO2H, CO2H, HOH, HOH. This is the classical one. This is a meso compound. So another is possible. OH, OH, H, H, CO2H, CO2H. Okay. So another is H, OH, OH, H, CO2H, 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 H, OH, H, OH. So logically, if I consider 2 chiral centers, so that means you are getting 4 isomers. But if you see this compound, and this compound, we call it, both are a meso compound. So we call both the compound are same. Okay. So this is only, we consider this is a 1, this is 2, and this is 3. So these two compounds are same compound. Clear? So this because this is a meso compound. Because meso compound, this case also you put a mirror here, you will get the same compound. This case you are putting a mirror here, you get the same compound. Okay. So this is a very interesting point I'm going to share. So there is a, if now, sorry, I have made a mistake. So there is another important point. These two have a relations of, so these two case these two are have a mirror image relationship. So 3 and 4 are enantiomer. Okay, 3 and 4 are enantiomer. 1 and 3 are diastereomer. 1 and 4 are also diastereomer. Clear? So this is very interesting one. Okay. Next, I'm going to explain the another interesting problems. Okay. So let's talk about the substitution is not the same. Okay. If I consider CH3 H beer, okay, H beer and ethyl. Clear? So they, you see, this is the one chiral center. There is another chiral center. Okay, but the connectivity on this chiral center is methyl group, bromo, hydrogen, and CHBr ethyl. But if you consider from this center, if you consider for this center, connectivity is hydrogen, bromide, ethyl, and this one. So that means it's not a symmetrical one. So this case, the formula will be only 2 to the power n. So that means 2 to the power. So you will get total 4. So whatever I have drawn, this is the 1. So there is another possibility is bromo, bromo, hydrogen, hydrogen, CH3 and ethyl. Okay. So this is the another one. This is the 2. So there is another possibility will be which one? CH3, ethyl, bromo, bromo, hydrogen, hydrogen. Clear? This is will be 3. And another one will be hydrogen, bromo, hydrogen, bromo, CH3 and ethyl. Now if I say what will be the relationship between 1 and 3, 2 and 4, 1 and 2 and 3 and 4? The answer will be 1 and 2 are mirror image relationship. 3 and 4 have also mirror image relationship. That means 1 and 2 are enantiomer. 3 and 4 are also enantiomer. Remaining all the relationship will be diastereomer. Enantiomer means there is a mirror image relationship, and their chemical properties will be same, physical properties also same. So you can't separate them easily. Okay, to separate, if you have two enantiomers, you have to separate by a chiral optical technique that is not included in your syllabus. How to separate them? Okay, but diastereomer have same chemical properties, but their physical properties will be different. Diastereomers have a physical properties have a different, like boiling point, melting point, so you can easily separate it. Okay, so by this way, I have shown here two. So how many chiral centers? Two centers, chiral center and similar type of connectivity and the different connectivity I have explained. So simplest one is a single chiral center, one chiral center. That cases only you will get two isomers. The formula will be 2 to the power n. So that case you can easily. So you can explain by this theory all the chiral isomers. Okay. There's a very interesting point. Sometimes these questions arrive in the exam. This is called ethylene glycol. Okay. So this kind of compound shows high boiling point. Okay. There is another interesting compound. This is CH2Cl, CH2Cl. This compound have a net dipole moment. Net dipole moment. Net dipole moment, if I written net dipole moment equal to 0. Explain. So I have given you two problems. One and this is another one problem. How can you solve this? So if you try to solve such kind of problems, the first one is if it is given such kind of compound, it's written high boiling point. How can you explain? And this gets given CH2Cl, CH2Cl, net dipole moment is 0. So how can you explain? So for explaining such kind of things, you need the help of Fisher projection formula, followed by you have to draw the Newman projection formula. For example, this kind of molecule not a chiral molecule. Okay, so basic structure will be you can draw like this way: hydrogen, 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 OH. You can draw many ways. I have drawn one of the Fisher projection. You can draw a lot of ways. There is no such problem is there. I am drawing directly from here to the Newman projection formula. So this is the Newman one. My IH is here. I have already explained in the last class also. Hydrogen, hydrogen, OH is there. Clear? So then the next carbon center is coming. So I'm talking about this one. That one hydrogen is there. That is the hydrogen and this is the OH. So this is the eclipse structure. I'm saying this is a eclipsed structure. Clear? So eclipse structure will be definitely unstable. So this kind of molecule try to prefer if you rotate 180 degree, what you will observe? You can draw like this way. This molecule try to stay. This is the one of the structural. So last class I have already explained. This is the staggered one. Okay. What I did, I have fixed the top one. I have rotated the back one. Clear? Now, if you rotate this molecule, so I am erasing this section so for better understanding. Okay. Okay. So it is not working. Let's go here. Okay, so okay, I'm putting on another slides. For better understanding. Okay, so if I rotate that molecule, just see the previous slide. I'm drawing this molecule. This is the eclipsed one. That one I'm rotating the 60 degree only 60 degree rotation. Then what you will observe if you rotate the molecule 60 degree. Okay, if you rotate the molecule 60 degree, what will happen? You will get OH. You will get OH, hydrogen, 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 hydrogen. So there is a possibility for, so this structure is called the Gauss configurations. This is a Gauss structure. Okay, so in the Gauss structure, there is a possibility for hydrogen bonding. All of you already known from your 10+2 level, hydrogen bonding, when there is a such kind of hydrogen bonding will be taking place. So there will be much more stability from the previous one. So this case, there is no such stability there in the staggered structure. So in the staggered structure, there is no such stability there. Eclipse structure always unstable. So when you consider for such kind of molecules, so they will definitely prefer to stay in this structure. Okay. So that means they will prefer to stay in this structure. So as a result, Gauss structure, as a result, strong hydrogen bonding, as a result, it will increase the boiling point of particular systems, ethylene glycol kind of bonding. So when such kind of problem will be there, immediately you have to draw this structure. But if you consider for this molecule, so if you consider for this molecule, what will happen in the case of CH2Cl, CH2Cl? We observed here, again you have to draw the the Fisher projection formula. Then we can draw chloride, chloride, hydrogen, 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 and sorry, I have written wrong. So this no, okay, this is fine. This is CH2Cl, CH2Cl. Okay, so now I'm directly drawing from here. I'm not drawing the Newman projection formula. The in general structure will be first the Newman one. Okay, that will be chloride here, hydrogen, hydrogen, then it will be hydrogen, then it will be hydrogen, and that will be chloride. Okay, so this is the eclipsed one. Now, if you rotate this molecule 180 degree, 180 degree rotation क्या मिलेगा आपको? You will get this compound. Chloride, chloride, hydrogen, 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 and hydrogen. So these give you idea because this is the most stable one. Chloride means that your dipole moment direction is that direction. That chloride is because it's electronegative. So it is a nullified between this chloride, their dipole moment. As a result, overall dipole moment, this chloride is that direction. So overall dipole moment will be 0. So basically, you are getting this all kind of things from the Newman projection formula. All kind of properties you can explain from the Newman projection formula. So because this molecule try to stay initially eclipsed, but they will prefer to stay in the normal condition in the staggered configurations. So this is a staggered structure. This is staggered one. Okay, this is called staggered structure. After 180 degree rotations, so you will get these structures. Clear? Okay, so next. Last class, I have already explained about how can you rotate from one structure to another flying wedge formula. This is a very interesting one, and this is called the lactic acids. Okay, so this is a lactic acids. H, OH, CO2H, CH3. So I have last class I have explained for the two center. Today I'm going to talk about the one center also because I have seen your post several times one center time wise formula is coming. Okay, so basically last class what I did, I can move any directions. Okay, because this is a if I move in that particular direction, then what you will get the structure will be like this way. You are moving that one, so this one will be your CH2, that will be your CH3. Clear? So I have told when you moving that particular direction, whatever may be the group will be there, that group will be up. So which group is there? OH. So OH will be up. And which group will be down? Hydrogen will be down. So this is the Fisher projection formula. This is the flying OH projection formula. This is very, very important for all of you. So you can check it. What I did. Remember again. So whatever the chain is there, whatever may be the group you are moving, any particular directions, that when you are moving that one, the reverse group, whatever group is there, that particular side, that group should be up. Always remember. Okay. And or sometimes it's coming, for example, conversion from flying wedge to Fisher or Fisher to flying wedge. Okay. Or Fisher to Sohor's, Sohor's to Newman projection formula. All of you should try by yourself because this is a very interesting one. Okay. So now I'm going to talk about the another interesting sections which is there in your this is the in your syllabus is there. So this one is okay. Okay, it's not working. Okay, so this section I'm going to talk about the conformation of different kind of compound and corresponding energy changes. So there is a lot of factors are there if you rotate, because if you consider the simplest molecule is this is called ethane. Okay, so if you consider this molecule in the 3D, this is also sp3 carbon, this is also sp3 carbon. Okay, so there is a lot of rotation is possible between these two carbon centers. If you rotate, there will be a lot of factors are there for the rotations, and that factors you needed. Factors means you need ultimately the energy. If you consider the energetically, if you rotation means it will change the energy. That may be higher and that may be lower, depends upon the different type of conformations. Clear? So here, when I'm going to the conformational energy diagram for such kind of molecules, I will start. I always try to prefer to draw such kind of molecule in a Fisher projection formula. So first, the simplest one is the ethane. Then I'm going to go to the next molecule. Ethane means this is the simplest one. I can draw like this way. Okay. So if it is the ethane molecule, now if I draw from here to the Newman projection formula of this one, you always have to draw directly to the Newman. And I have already explained my IG is here only. So that carbon will be your top one. Okay, the bottom carbon will be this one, hydrogen, hydrogen, and hydrogen is there because all the substitution is the hydrogen. Now, if you rotate the molecule, you have to fix the top one, rotate 60-degree operation. On operations, you are doing the 60-degree operations. Okay, I'm considering this is a structure number 1. Then the structure number 2 will be this. I'm fixing the top one, rotating the back one. All of the hydrogen. Clear? Now I'm rotating again 60-degree. Then what I will get? Okay. So then again you are getting a hydrogen, hydrogen. Okay. So this structure we will consider if it this one is structure, this is a 2, so that will be 3. So that means this is a 0-degree structure, this is a 60-degree, this is a 120-degree structure. Now you rotate again 60-degree. Then what you will get? Clear? So this is an I am considering this is structure number 4. And what you get after 180-degree rotations. Now again you rotate this molecule 60-degree. So then what you will get again? Here all the substitution is same. Okay, that's why you are getting always the same type of structures. There is similarity there. So this is after 240-degree, you will get this structure. I will consider this is structure number 5. Structure number 5, 4, it's very important. Now I am rotating again 60-degree. Then I am getting this structure. So this is 300-degree. Total operation is already 300-degree done because you are rotating 60-degree again. And this is structure number 6. Now, if you rotate again 60-degree, you will get the structure 1 again back. 360 is again 1 back. Now, if I draw the energy profile of diagram of this kind of molecules, this is called, this kind of structure is called, this is called eclipse structure. I have already explained several times. This is eclipsed. This is called here, all structure here looking staggered. But there is a lot of case, lot of different name will be arrived. So again, this is eclipsed. Again, this is staggered. Again, this is eclipsed. Again, it is staggered. Again, it will be eclipsed. So eclipsed means one hydrogen and another hydrogen, they are facing just each other from a very close directions. The angle, the one angle between this, the angle between this is zero. This is called actually the dihedral angle. The dihedral angle is zero here. So when this all the angle is the dihedral angle. When the dihedral angle is zero means they are facing very closely to each other. So that will be energetically less stable compared to the staggered one. Now, if I draw the energy profile diagram of this molecule, so if I draw the energy profile diagram, okay. So what do we see here? I will draw like this one. So I'll write here, this direction will be your dihedral angle. Okay, this direction is the energy. Clear? So this is a 0 degree. Then this is 60 degree. This is 120 degree, 180 degree, 240 degree, 300 degree, and this is 360 degree. So if you see my previous one, the 0 degree one, 0 degree will be the eclipse structure, which is the energetically little bit higher in energy. 60 degree is the staggered one, and this is the structure number 1. 60 degree lower in energy. Again, you go to the 120 degree, the energy is higher. Again, you are going the 180 degree, the energy is lower. Again, you are going to the 240 degree, the energy will be higher. Again, you are going to the 300 degree, the energy will be lower. Again, you are going to the 360 degree, the energy will be higher. So you can just add all the points you are getting here. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 1 again. Clear? So that means you are getting a 2 different type of level of energy that you can see in the previous case also. You see here. So you are getting this one is this 1, this 3, this 5, and again 1 are in the one types. 2, 4, 6 are another types. If you see here, 1, 3, 5, and 1 again another one types, and 2, 4, 6 are another types. So that means those who are stable, they have a lower in energy. Those who are little bit unstable, they have a little bit higher in energy. So this is the simplest molecule I have drawn. But in your syllabus, we have another molecule which is butane. Butane means you have a CH3, hydrogen, 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 and CH3 molecule. Clear? So it will be exactly same theory we follow here. I'll draw very quickly. Okay. Hydrogen, hydrogen, CH3. My eyes is here only. I'm visualizing my molecule from that particular directions. Okay. Your CH3 group will be here. Hydrogen, hydrogen is here. Okay. Now I rotate 60 degrees. So this is a structure number 1. Then what you will get? You will get this here CH3, CH3, hydrogen, 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 hydrogen. This is a hydrogen. Okay. So this is a structure number 2. This one is called eclipsed. This is called staggered. Sorry. This is not staggered. This is not staggered. This is called gauge structure. Okay. This is new term. This is not a staggered structure. Now you rotate the molecule again 60 degree, then what you will get? This is a very interesting one. So you will get your CH3 is fixed here, hydrogen is here. This is a CH3, this is hydrogen, hydrogen, hydrogen. This structure is called partial eclipsed. Partial eclipsed, why? Because you see in the structure number 1, 2 CH3 and CH3, their dihedral angle is 0. They are facing equally from, because 2 are the bulky group. Now here you can see one CH3 is facing to hydrogen, another CH3 is facing to hydrogen. So that means there is a little bit lesser in strain compared to the structure number 1. So this is very important. So this is structure number 3. When the dihedral angle is total 120 degree, because you did the 60 degree and 2 times 60 degree operation you have done. So that's why it's a 120 degree. Now again you rotate the 60 degree, then what you will get? This is called CH3, CH3, this is CH3, hydrogen, 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 hydrogen. This is called staggered structure. This is staggered. Okay. So this is structure number 4. Clear? Now you did the again operation. So this is after 180 degrees. So that means it's a 180 degree you reached. Again you did the 60 degree rotations. Then what you will get? So you'll get CH3, hydrogen, CH3. I'm just rotating all the times the below the back side one, not the front one. Okay. So this one again, it is called partial eclipsed. Partial eclipsed, and it will be after 240 degree and the structure number 5. Now you did again 60 degree operations. Then what you will get? This is CH3, this is CH3, hydrogen, 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 hydrogen. So this structure is structure number 6, and this is called Gauss again. So this is a So this is a Gauss structure. Okay, I am written upon Gauss structure. Okay. Okay. Now if you rotate again, I'm coming directly to here. Now again, if you rotate again 60 degree, so what you will get? You will get back to 1. So this is a 360 degree rotation 1. You will get back the structure number 1 again. So that means you will get the eclipsed one. This is very interesting one. Okay. So here, can anybody explain? So which structure will be the more stable one? Definitely the staggered one. The structure number 4 would be the most stable one. Which one will be the least stable? That means that will be 1. Means when the angle is 0 degree, when the angle will be 60 degree, that will be the सबसे least stable. So which one will be their least? The least means this will be the higher in energy 1. So then your this partial eclipsed one, that means structure number 3 and structure number 5 will be the little bit higher in energy, less energy compared to the 1. Okay, and in between will be the most stable, and the in between will be the structure number 2 and structure number 6. I will draw the energy profile diagram, then you can better to get all the points. Okay. Okay, let's see what happened. I'll draw the energy profile diagram. Here, this is the energy. And this side is again dihedral angle. This is a dihedral angle. Okay. So first is the 0, means 0 degree you did the rotations. Then 60 degree, then 120, then 180, then 240, then 300, then 360. Clear? Here I am drawing few energy level for better understanding. If you are smart enough, you can't draw that kind of line, not necessary for you. But for me, it will help you to draw, if you draw the energy level diagram like this one. Clear? Now I'm changing the color for better to understanding. So I have told 0 is the सबसे least stable, the structure number 1. Okay, least stable means higher in energy. You can see here. Okay, then 60 is the 60-degree rotation, which is not the most stable one. Which is not the most stable one. Okay, so that means it will be like this. 120 degree is not the least stable. That means it will belong to here only. Clear? 180 degree is the सबसे ज़्यादा stable one. That's the most stable one. So it is staying here. And you can compare from this one. And 240 each belongs to here only. 240 each belongs to, just check 1 minute. 240, okay. This is a partial eclipsed. So 240 definitely here. 240 is here only. So this is a 240. Okay. It will be so this is a 241. This is a structure number 5. Then 300 will be here only. It is very similar to 2. This is structure number 6. And definitely 360 degree will be similar to 1. So now you just add all the points. Clear? From here you are getting clear idea. The 4 is the most stable one. Then the next stability is the 2 and 6. Then the next stability is 3 and 5. Then the less stable one is the only one when the angle. The corresponding angle you can find out from here and you can get the diagram. Completely explain the property. You can consider any kind of molecules and you can draw the any molecule in the Fisher projection formula. Then you convert it to any other systems and immediately you will get these systems. Okay. So here I have already covered whatever is there. EZ, RS. I have just missed one of the points which is in your syllabus is there in the stereochemistry section because it's a stereochemistry is vast. I have covered only the topic. If you have any kind of doubts, you can send a message. I will try to give you the answer back in the team. So stereochemistry contains a lot of sections, so it's not easy to cover in very short time frame. Okay. So there is another interesting point is there that I'm going to explain. Sometimes in the exam, its question is arrived. Okay. So there is another type of name is there, which is all of you study, maybe the D and L. The D and L, it's a very similar type of nomenclature in the R and S, but D and L is the very not so much applicable for a lot of molecules. It's only specifically particular type of molecule we can explain. This is a D terms coming from dextrorotatory. Dextrorotatory. L is coming the levorotatory. Okay, so it's only few types of molecule there. That particular cases you can explain the dextrorotatory. For example, this is a lactic acid. So let's for the theory is you have to draw the longest alkyl chain in the vertical line. So if I consider lactic acid, the formula is CO2H, CH3, H, OH. CH3, CHOH, CO2H. So the longest chain will be the 3 carbon one I have drawn in the vertical line. If OH group is in the right side, if in the Fisher projection formula, if OH group in that right side, then we call it D. If OH group, I am drawing the another molecules. I'm drawing the another molecules for better understanding. CO2H, OH, H, CH3. If OH in the left side, then we call it levo-rotated L. The term is coming L. So this is only the first criteria will be you have to draw the longest chain, carbon chain in the vertical lines. Then you have to consider the last one, because if there is multiple connectivity there, lot of connectivity with the last one, suppose this is the last one, that case is the highest priority group in the which side, either right side or left side. If it is in the right side, then only you can say it is a dextrorotator. If it is a left side, so specifically actually we can explain lot of sugar molecules. That cases we use such kind of nomenclature to identify their positions, and we can identify which group is which particular place. Okay, I'm just living here only in the stereochemistry section, but I will start the another interesting sections which is there in your syllabus, which is we have incorporated this year. All of you studied, which is called the substitution reactions, elimination reaction, and rearrangement. Okay, this is very important. Substitution reactions, all of you already studied in the 10+2 level. This is called one is called SN1, another is the SN2. SN1 means S is coming from substitutions, N is coming from the nucleophilic, 1 is coming actually specifically the order of the reactions. Okay. Substitution nucleophilic, the orderity is 2. Nucleophilic substitution, its orderity 2 means it's called bimolecular reaction. This is a nucleophilic substitution, this reaction. Unimolecular reactions. Okay, so all of you already studied the basic concept of SN1 and SN2 reactions. SN1 reaction actually, if you consider any kind of SN1 reaction, actually it is passes through a carbocation pathway. Let's consider a example, because here you need a lot of stereochemistry. That's why I have started in the last part of this section. Okay. So if I consider, I'm drawing the flying wedge formula. Okay. If I consider A, B, B and C and X. Okay. This molecule, when you added in particular conditions, X is removed from your systems, then what you will get? A, B, C and the positive charge. So this is a carbocation. If you passes through, so that means this reaction, if you started from here, you are getting this product. How many component involved? Only one component is involved. Okay, that's why the term is coming unimolecular. Okay, now the next step, this is the step 1, and this is the RDS. RDS means rate determining step. Okay, now in the step 2, what will happen if Y minus something, Y minus will attack. If something Y minus is attacked, what will happen? Again, the same problem. Okay. Something y minus is attack. There is a two possibility. One is from that side. If I consider this attack is path A, so then what you get? A, B, C, and Y. Clear? Which is very similar to your starting materials. If y minus is attacking from path B, okay, then what you will get? Y, A, B, and C. Clear? So this is the step 1. This is the step 2. I have already told the step 1 is the RDS, means rate determining steps. That step, how many components involved? Only one component. That's why this is called the SN1, nucleophilic substitution 1. Why substitution? Because X group is removed, Y group is incorporated. X group is substituted by Y group. That's why it's called substitution reaction. Clear? Now the important point, the stereochemistry. Suppose I'm considering this is a R compound. So definitely this will be R. Okay. And this should be S. And you will get the R plus X in the 50-50 mixture. 50-50 mixture of R plus S. Okay. So this is the biggest criteria for a nucleophilic substitution unimolecular reactions. So what you will get? You will start from a particular stereoisomer and you will finally get a racemic compound at the end. There is a several factors is there. I will explain one by one. But this is the first one. What is the process? Now let's consider the same type of example. Okay. Let's consider A, B, C, X. Here, X will be leaving group. Leaving group means substituted by something, and Y minus is entering. So it's a nucleophile. That Y minus approaching from that side, and X group is removed. The biggest criteria is X and Y approach to each other will be 180 degree. This is the first criteria. Okay, so that means 180 degree means Y will be approaching from the back side. And what will get? A, B, C, Y, and X. This is the transition state. This is also RDS. Why this is RDS? Why this is bimolecular? You can see RDS means rate determining step. Actually, this is the step which actually directed your reactions, which direction it will be gone. Clear? This is the biggest point. And another important point, how many component is involved? So this is the one component and this is the another component. Two component is involved. That's why it is a bimolecular reaction. And this is processed through this transition state. Okay. Now, next step, what will happen? This X group will be removed. Then what you will get? Y, A, B, and C. So that means if you started with the R compound, what you will get? S. Or if you started with the S compound, what you will get? R. Okay. So this is the step 2. Step 2 is not the rate determining step. This is the step. So this is called inversion of configurations. This is called inversion of configuration. So this is a very interesting one. Inversion of configurations. How inversion is taking place. Clear? So this is the basic condition for a nucleophilic substitution SN1 and SN2 reactions. There is a lot of factors are there. In your exam, many times such kind of problem arrived in your exam. If you consider, I will give you a series of compound. Okay, CH3, 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 Br. This is a tertiary compound. CH3, CH2, Br. CH3, CH3, HBr and CH3Br. So I have given 4 compounds. This is a compound number 1, compound number 2, compound number 3, compound number 4. So as I have already explained previously I have explained that SN1 reactions proceed by carbocation mechanism. So from these 4 examples, you can easily, all of you already studied, the tertiary carbocation will be much more stable. So this one will be, when it will be bromide group will be removed, you will get a tertiary carbocation which is stabilized through inductive effect and the resonance effect in the hyperconjugative effect, not resonance, hyperconjugative effect. So it will be much more stable. So more greater the stability of the carbocation, greater will be the preference for SN1 reactions and lesser will be the chance for SN2 reactions. Now this one will be the highest SN1, then this one will be the second highest SN1 reaction, then it will be the third highest, and it will be the least SN1 reactions. Clear? Because there is no, only if it is a CH3 plus carbocation will form, there will not so much stability will be there. So it will be the least one. Clear? So this is the biggest one. Now, if you consider the SN2 reactions, the reverse one always prefer the less substituted one will be preferred, because the when the any nucleophile will be attacked, it will be preferred always the less substituted one. The less substituted one will be this one. That means least SN1 means highest SN2. Then this will be the second highest SN2. Then it will be the third highest, and this will be the least SN2 reactions. So this problem we can draw by a diagram. Okay, we can draw a diagram and we can explain very easily. So I am drawing here CH3Br. Then I am drawing the CH3, CH2Br. Then I am drawing Br. That means hydrogen, methyl, and this is methyl, Br. Okay. Now I have already told this one is the highest SN2 reactions. This one is the second highest SN2 reactions. Now this one will be the third highest. This one will be the least. If I consider that this is SN2 reaction, it will be follow like this one. Clear? Now if I consider the reverse one means this one, this is a SN2 reactions. So which one is the highest SN1 reactions? That will be the highest SN1 reactions. That will be the second highest SN1 reaction. That will be the third highest SN1 reaction. That will be the least. Clear? So you can get the idea. This is a SN1 reaction. Their direction is the rate of the substitution reaction. Clear? Rate of the substitution. So you can easily get which type of compound belongs to the which particular area of the curve. Clear? There is another important factors, several factors. All of you should study the the whatever study material we have sent, lot of other factors are there. Solvent defect, polar protic. Polar protic means methanol, waters, ethanol, such kind of solvent. SN1 reaction will be preferred. This SN1 reaction will be preferred in the polar protic. Polar protic, why? Because carbon cation will be getting the stability of this polar protic solvent. Polar protic solvent क्या होता है? Methanol, ethanol, and many more like this. Okay. Polar aprotic solvent will prefer in the SN2 reactions like DMSO, dimethyl sulfoxide, DMF, such kind of cases, SN2 reaction will prefer. Okay. There is lot of others, depends upon the nucleophile, depends upon the living group. SN1 and SN2 reaction rate also dependent. Okay. So I hope I'm able to explain a lot of things. Next, I will just cover the elimination reaction, then I will stop today. Okay. If whatever remaining is there, Saran sir will continue in the next class. So there is another interesting reaction is the elimination one. Elimination also follow elimination. We call it elimination unimolecular and elimination. In your syllabus, only E1 and E2 is there. There is another is the E1CB. Also reaction is there. So basic theory is again same. Elimination means more than one center should be there. Okay. Let's consider like this way. Sorry. If I consider this is A, B, C, D, when you added a base, that base will attract, take the proton, it will attract and it will remove. Then what you will get from here? You will get a double bond like this. Whatever dotted line that will follow the same side, whatever bold line they are staying in the another side. Clear? Why this is a unimolecular reactions? That means unimolecular. This is the basically elimination reaction I have wrote. Okay. Unimolecular reaction means again leaving group will be removed, carbocation will be formed. That will be the RDA steps. I will explain in the another slide. Better. So this is the, if I draw L hydrogen, A, B, C, D. Okay. Now leaving group leave first. Okay. L will be removed, minus L. Then what will get? You will get hydrogen, this, and C, D, and positive charge A, B. Clear? So that means this is the RDS. Means when the leaving group is removed, that is the carbocation we formed, that is the RDS. Next step, what will happen? You have added some base. So base will take the proton. This base will take the proton and it will make a double bond. Then you will get A, C, B, D. This is the step 2. This is not the RDS. So RDS means the rate determining step. This is the slow one. So removal of the leaving group is the important one. So how many components involved? Only one component is involved in the when the leaving group is removed, and only carbocation is formed. So that is again, that's why it is called a E1 reaction. Now in the E2 reaction, what will happen? That is the one I have drawn in the beginning. This is the, so base is coming directly taking the proton, and leaving group is removed. So there should be an intermediate step. So where base, hydrogen, and everything will be involved. That particular step, 2 component is involved. That means you will get from here like this way. This is a living group is removed and remaining will be same. Okay. C is there, D is there, A is there, and B is also there. So this is the RBS. Then you are getting the product. So I have written dotted line. Why? Because base is attacked. I mean base will take this one. All are involved in this transition state. Okay, and L is removed. How many component is involved? Base is a one component, and this is another component, and this is the RDS. That's why it is called bimolecular reactions. Then the next step is the this is the first step. You are getting the product. So that's why this is called the bimolecular. Again, this is again all the property. It will follow the same strategy. How living group will be removed, how the other component is involved. That is there. All other point is there. So I'm stopping here only. If you have any kind of questions, you can send to me and I will try to give the answers. I think good luck for your mid-semester exam. And whatever remaining section is there, there is another class. Saurabh sir will discuss. If I get the time, I will also discuss. Okay, so thank you everyone.